So in this video, I'm going to briefly talk about the probabilistic complexity classes, including RP, and then explain the proof for the Valiant Vazirani theorem, which is a very classical theorem in the complexity theory. So firstly, the probabilistic complexity classes is a set of classes where you have an algorithm A for a problem, and the algorithm takes in an input X and also a sequence of random bits R, and then based on the X and R, it outputs the correct answer for X with some probability. So that's the probabilistic complexity classes. Now, RP belongs to the probabilistic complexity classes. So RP is a set of decision problems such that there is a polynomial time algorithm A and a polynomial P, such that for each instance X that is in the language, the algorithm will answer correctly more than half of the time or equal to half of the time. Then if the instance is not in the language, then the algorithm will never answer yes to this instance. So it will always reject instances that is not in the language, but it will sometimes answer correctly, but sometimes answer incorrectly for instances that is in the language. Now we have this theorem 1, which says that RP is contained in NP, and why is that? So suppose we have an arbitrary language LR that is in RP, then for any instance W of the problem, we can say if W is in LR, then there is a random sequence R for which the algorithm answers yes. And if the instance W is not in LR, then there is no random sequence that will trick the algorithm to accept the instance W. So this is very similar to what we talked about in NP, right? So we say a problem is in NP if there is a polynomial time verifier such that for each instance that is in the language, then there is a witness C such that W and C is accepted by the verifier. And if W is not in L, then there is no such witness that will trick V to accept, that will trick the verifier to accept. So we can see that the random sequence R here serves as the witness for the verifier. So then we can build a verifier for the language LR. So we know RP is contained in NP. Now you might recall that the set problem is NP complete. So it is hardest amongst all NP problems in the sense that any problem in NP can be reduced to a set problem. And there is a variance of the set problem called the unique set. So the unique set problem accepts a Boolean formula F as input and returns yes if F has exactly one satisfying assignment, no if F has no satisfying assignment. And either yes or no, we can't guarantee the result. If F, the input that we give it, is does not have a unique satisfying assignment, so it has more than one satisfying assignment. And this kind of problem is called the promise problems because we promise the algorithm something about the input. In this case, we promise the formula has at most one solution, and we ask the algorithm to return the correct result given the promise is fulfilled. A consequence of the Valiant Vazirani theorem says that if we can have a polynomial time algorithm that solves the unique set problem, then we can have a randomized polynomial algorithm for the set problem. So the set problem will be in RP as described above if we have a polynomial solver for the unique set. Problem. And since set is NP complete, we also have NP is contained in RP. So we can have NP equals to RP, because the theorem 1 says RP is also contained in NP. So we have this equality if we have the polynomial solver for the unique set. Now we'll proceed to prove the Valiant Vazirani theorem. So the Valiant Vazirani theorem says that given the Boolean formula f in conjunctive normal form, we can construct in polynomial time a set of formulas f1, f2 to fm, all in conjunctive normal form, such that if f is satisfiable, then with probability greater than 1/8, one of fi is uniquely satisfiable. And if f is unsatisfiable, then all the formulas that we have constructed are unsatisfiable. So the proof can be broken down in the following steps. Step 1, we will show how to build a Boolean formula gadget called a hyperplane. Then step 2, we'll use these gadgets or hyperplanes to construct a set of formulas fi. And then step 3, after the construction completes, we will prove that if f is unsatisfiable, then all the constructed formulas are also unsatisfiable. And in step 4, we will show that if f is satisfiable, then with probability 1/8, one of the fi is uniquely satisfiable, or with probability more than 1/8, that one of fi is uniquely satisfiable. So let's do step 1 first. Suppose we have the input a Boolean formula f, which contains x1, x2, xn as the variables. Then let S be a subset of these variables. A hyperplane eta S, which is the gadget we're trying to build, is a Boolean formula in conjunctive normal form, which states that there are an even number of xi in S that are true. So we'll use an example to show how eta S can be constructed from S. So suppose n is 4 and S is a subset of the variables, and it includes x1, x2, and x4. So we build eta S as y0 and x1 double implication y0 plus x1 and y2 imply x2, then y3 and y4. Okay, so this symbol here is the bidirectional implication, and this symbol here is exclusive OR. So this Boolean formula can be rewritten as the following set of equations. So if we regard all the implication as equal, and if we regard all the exclusive OR as addition, then we can say y0 is 1, y1 is y0 plus x1, y2 is y1 plus x2, y3 is y2, y4 is y3 plus x4, and y4 is 1. So then, if we solve this system of equation from bottom to the top, then we can see that 1 is y4 equals to y3 plus x4 plus y2 plus x 4 equal to, and then equals to y1 plus x2 plus x4, and in the end we'll have 1 plus x1 plus x2 plus x4. So if we have 1 equals to this, then this is saying x1 plus x2 plus x4 is 0 when we mod 2. So this is equivalent to saying there are an even number of variables in S that are 1. So this is step 1. Now for step 2, we're trying to construct the set of formulas Fi using the gadgets that we just described. So say the original formula F contains variables x1, x2 till xn, and we randomly choose n plus 1 random subsets, and we call them Si from the set of variables, and we say F naught is F, and then we let F1 to be F and eta S1, F2 equals to F and eta S1 and eta S2. Then we have Fn plus 1 equals to F and eta S1 and eta S2 all the way till eta Sn plus 1. Okay, so this is the construction for the set of formulas Fi, where I ranges from 1 to n plus 1. Now for step 3, recall that we just finished the construction for all the formulas. It's easy to see that because F occurs in all the formulas that we constructed, if F is unsatisfiable, then none of these formulas is satisfiable. So then we proved this part of the theorem. So the set of formulas that we constructed satisfied this part of the theorem. Now we only need to show that if F is satisfiable, then with probability more than 1/8, one of the formulas that we constructed is uniquely satisfiable. So we have step 3, if F is unset, that's solved. Step 4, if F is satisfiable, then we want to show with probability greater 1/8 that one of Fi is uniquely satisfiable. So here's how we are gonna show it. Let T be the set of satisfying assignment of F. And the order of the set is D. So this is the number of set assignment for F. And we're going to show that with probability more than 1/8, the formula Fk plus 2 is uniquely satisfiable. So remember, Fk plus 2 is the formula F and eta S1 and eta S2 all the way till eta Sk plus 2. So let T be an arbitrary satisfying assignment for F. Then we want to calculate the probability that, given that we have randomly chosen the sets Si, the probability that T is the only satisfying assignment of Fk plus 2. And this probability can be broken down to be the probability that T satisfies Fk plus 2 times the probability that other satisfying assignments T prime not equal to T does not set Fk plus 2. And these two probabilities are independent, so we can directly multiply them. And if we refer to the first probability as P1, second one as P2, so we will look at each probability respectively. So P1 is probability that for all I, eta Si T is true. So this is saying if T satisfies Fk plus 2, then all the gadgets that we built needs to be satisfied. And because T already satisfied F, we can ignore that. So then this probability will become Fs eta St equals to true to the k plus 2 power, because there are k plus 2 gadgets and each gadgets are independent, so we can say that this is the one probability and done k plus 2 times. So then let's recall the gadget the gadget is satisfied when there are an even number of true variables in S. So we say this is the probability that S contains even number of true variables. But then what is this probability here? So there are two cases that we want to consider. Case 1, we have the T, which is the satisfying assignment for F, assigns all the variables to false. Then we know, because there is no true variables, no matter what subset S is, it always contains 0 true variables. So it always contains an even number of true variables. So the probability, let's denote this as E. So the probability of E will be 1 in this case. For the second case, if T is not all false assignments, then there must be some variables that is assigned to true. Let's first assume that the set S only contains true variables. So if that is the case, suppose the true variables are xr1, xr2, xrm minus 1, xrm, where m is the number of true variables in T. Then if S only contains true variables, then the number of different choices for S will be basically 2 times 2 times 2 for the first r minus 1 variables. But then for the last variable, because we're trying to build a set that contains even number of true variables. So because S only contains true variables in this case, we want to construct a set that contains even number of elements. Then the last element has only one choice, to be either in S or not. So in total we have 2 to the n-1 such subsets S. But we know S actually contains more variables than the true variables. So if we consider the more general case, so X contains both true variables and false variables. The number of false variables can be 0, or there can be some false variables. Then because we know that we can build this number of subsets that only contains true variables, and the subsets that contains both true variables and false variables are basically these subsets appended with some false variables. So we can freely choose the n-m free false variables, and then append it to the 2 to the n-1 true variables. So then we get 2 to the n-1 sets. So because the total number of subsets of the variables is 2 to the n, and we have 2 to the n-1 choices for S, which contains both true variables and false variables, and the number of true variables is even, then the probability of choosing an S that contains an even number of true variables is a half in this case. So because in case 1 the probability is 1, and in case 2 the probability is a half, we can say that the probability in general is at least a half. So because P1 is this probability to the k plus 2, so it is greater or equal to 1 over 2 to the k plus 2. Now we just need to show probability 2, which we say is the probability that for all t prime in T that is different from the satisfying assignment T that we chose in the beginning, then there exists I such that eta si t prime is not equal to eta si t. So this is the unique requirement for T. T is uniquely satisfying F. Because we're saying for any T prime that is not T, there is some gadgets that's not satisfied by T prime, because we already said the gadgets are all satisfied by T. And this probability can be further written as 1 minus the probability that there exists some T prime in T different from T, such that for all I, eta si T prime equals to eta si T. So we're taking the complement. We're saying this probability is equal to 1 minus the probability that the thing we don't want to happen, which is some satisfying assignment that's different from T actually satisfies all the gadgets. And this probability can be further written as union, because the total number of satisfying assignment is T, and we exclude the chosen satisfying assignment. So we have T minus 1. then we can say this probability equals to 1 minus t minus 1 times the probability that a randomly chosen t prime from the set of satisfying assignments that's different from t satisfies all the gadgets as t does. T can be bounded by, I actually forgot to say that. So here when we say D is the number of satisfying assignment of F, we're also assuming that D is between 2 to the k plus 1 2 to the k for some k that is an integer, and it also should be less than n minus 1. And we can find such k because D must be less than or equal to 2 to the n. So then using this constraint, we can say that this part is, so because D is less than or equal to 2 to the k plus 1, so T is equal to D, so the magnitude of T minus 1 is less than 2 to the k plus 1. So then what is this part of the probability? We want to consider the individual cases. Eta S T prime and eta S T. There are 3 cases. So case 1, eta S T prime. So T prime is all false assignments. And because T is different from T prime, T is not all false assignments. And in this case, the probability that eta S T prime is 1 and eta S T prime is 1 is 1 times a half, based on what we have proved for probability 1. Because if it's all false assignments, then there must be an even number of true variables. And if it's not all false assignments, then there's half of the time we have an even number of true variables. Then what about the probability? Probability that eta S T prime is 0 and eta S T is also 0. Oh, so I shouldn't have said T prime here. Okay. So that is 0 because eta S T prime is always 1 in this case. So for case 2, we have the opposite scenario. So T prime is not all false assignment, but T is. So then, similar to what we have above, it's a half times 1, and this is 0 here. So for case 3, we have T prime not equal to all false assignments, and T is also not all false assignment. Then the probability of eta S to be 1 is a half, and a half here, and this is also a half and a half. So we can see in all 3 cases, the probability that eta S T prime equals to eta S T is a half. Like this is a half, second case is a half, and the third case is a half. So we know this here is a half. So P2 is greater than 1 minus 2 to the k plus 1 times a half to the k plus 2. And this equals to a half. So P2 is greater than a half. And put them all together. Remember, we are solving for the probability that T is the only satisfying assignment for Fk plus 2. P1 times P2 to the k plus 2. So this equals to 2 to the k plus 3. And now because T is what we have chosen in the beginning, but we know there are the number of satisfying assignment for the original formula F. So the total probability that Fk plus 2 is uniquely satisfiable equals to the probability that there exists some T in the set of all satisfying assignments such that T is the only satisfying So this is equal to the probability that there exists some satisfying assignment in the set T, such that T is the only satisfying assignment of Fk plus 2. So this is greater than T times 2 to the k plus 3. Which is greater than or equal to 2 to the k over 2 to the k plus 3. Here we're using the fact that D is greater than 2 to the k or equal to. So then this is 1/8. So we have shown what we have set out to do, which is showing that when F is satisfiable, then with probability more than 1/8, one of Fi is uniquely satisfiable, which is Fk plus 2 in this case. So by now we have proven the Valiant Vazirani theorem, and how does that relate to what we said in the beginning about the set and unique set problem? So we said that the set problem can be solved by a randomized algorithm. If we have a solver for the unique set problem. So we will show this by constructing such a random algorithm that runs in polynomial time. Suppose we have an instance F for the set problem, then we can build a set of formulas Fi using the Valiant Vazirani theorem. And it has the property that one of the formulas in the set will be uniquely satisfiable with probability more than 1/8. Suppose we repeat this procedure for 6 times, so we build 6 sets of such formulas, then the probability that all of the formulas have no uniquely satisfying formula is 7/8 to the 6. So with probability 7/8 to the 6, which is less than a half, we'll be rejecting f. If f is satisfiable, with probability more than a half, we'll be accepting the instance f correctly. If f is not satisfiable, then all the variables fi are not satisfiable, so we'll be rejecting f correctly with probability 1. And therefore, the algorithm that we built satisfy the requirement for the RP algorithms. So then we can say the set problems is in the class RP if we have a solver for the unique set.